So I'm going to tell you briefly about the LSST database story. This is the future project, unlike the projects that you just heard about. So what is LSST, or Large Synoptic Survey Telescope? It's a ground-based optical survey with a 3.2 gigapixel camera that will be taking images every 15 seconds, every night for 10 years when it's live. So it will generate about 15 terabytes of just raw data every night coming from Chile, Cerro Pachón, and then sent to US for analysis, real-time analysis. 8.4 meter mirror, so very large mirror that has already been fabricated, and the camera is built at SLAC, so is the database system. In terms of timeline, we are still in R&D, and we are doing data challenges. We will be switching to construction sometime in the middle of next year. Once we pass the final design review, which is scheduled for next month. It was keeping us busy recently. And the operation is scheduled for 2022 until 2031, and then obviously analysis will continue for another 10 or so years. So we are really talking about quarter of a century, if not longer. So what is the challenge? In terms of the numbers, when we just run it through the spreadsheets, we can see the numbers reaching 82 petabytes. That's just the database. I'm not talking about images at all. That's another 60 or so petabytes compressed. So the 82 petabytes is all data releases compressed with all the indexes, single copy. If we look at the individual table, we are talking about something like 50 trillion of rows in one table. That table will have about 2 petabytes. And to aggregate this KO bandwidth that we are designing for, just for the user data analysis, this doesn't take into the account any data preparation, is on the order of a quarter of a terabyte per second. So I was interested to see earlier in the morning when Jeff was saying that their larger cluster is 100 gigabytes per second, the I/O. So we are designing for 2.5 more. However, this is for the future. It's not today. And the second challenge is the complexity. So it's not just about the numbers. Numbers are usually easy. You can store a petabyte very cheaply those days, or 80. But we have a wide range of queries, ranging from interactive queries, which are relatively easy, just time series of an object or a small area of sky. But then the difficulty progresses. We are expecting very complex queries running concurrently at the same time across the full sky, the whole data set, that are doing temporal correlations or spatial correlations. The queries that look for near neighbor across the whole sky are actually quite challenging in many ways. We are looking for outlier detections, various aggregation statistics. This is just an example of some queries. So things like find me galaxies in the dense region. Different people can define dense regions differently. Or near neighbor, or find me objects that have time series similar to a given one. How do we compare time series? So this is the kind of queries that we will have to deal with. So we think that we need something like the database plus. So it's not just a plain database with plain SQL interfaces and so on. But it's clear that we definitely need the indices for fast access. We need joins because we'll have different tables, pretty large tables, tables for individual observations, tables for summary information for astronomical objects, and so on. We will need group bys, we will need sorting, speed of the database, all that. What helps us is we probably don't need transactions in most cases because our data is read-only once we release it for various reasons like reproducibility. But we do have complex analytics. So what kind of database we are talking about? So as I said earlier, we are talking about the tens of petabyte scale, scaling to hundreds of trillions of rows. It needs to incrementally scale because we will keep adding data as we collect more. Obviously, we need fault recovery, so it better be distributed. But just one small observation. Notice that we have spatial correlations, so we can't simply divide space into, you can't divide sky into chunks and just distribute them randomly because you're looking for neighbors, and this neighbor, if you're near the edge, the neighbor can be on the other side and the other partition, so you have to take care of this. So that actually complicates things. We will have multiple table scans going at the same time. And the speed of scans for different tables will vary, but at the same time, we want to join those tables from time to time, so we have to take this into the account as well. And spherical geometry is quite complex. This is quite different from what most of you are working with. So things like the wraparound. Remember this globe I showed at the very first slide. So we have the issue of wraparound. 360 and 0 are actually close to each other. Polar distortions. People are looking for distances. They are dealing with various shapes and very complex regions, the polygons that are describing how the galaxy looks like and so on. And we have to take care of this. And the time series type analysis, how do you compare time series? How do you do it in SQL? And yes, and we have to do it for decades, and we don't have that much money, so it better be at the low cost. So what really are we asking for? What are we trying to build? We need the scalability and fault tolerance similar to what the Hadoop is doing, Bigtable and this sort of things. We need the features of Teradata for the price of MySQL. Actually, it's better if it's community edition price. We need the support for spatial features that are better than the top-notch systems. The Q3C, the partitioning that Postgres has, or Oracle, the extensions, that's just not good enough. It has been tried. We also need partitioning with overlap because of the reasons I mentioned earlier, the near neighbor type searches. And we need support. We need to support advanced analytics. And some extra goodies would be nice, like the resource management. We don't want a single user to take over the entire system, obviously. Partial results, if the query goes through the entire data set, all the 2 petabytes, it would be nice to start streaming the data as we go through individual chunks of the data. so many features like this. What we do have is time, because as I said, we are starting production in 2022. But we do need to have a running proof of concepts today. And we are actually running them. So our philosophy is basically reuse where we can, what we can, ideally open source, build what we have to, and release it as open source, and then isolate things in between and keep the narrow interfaces, because we know that software doesn't last for too long. So in reality, we are using MySQL, we are using XLDB, which we just heard about. So we have a lot of features like execution engine indices, scanning, sorting, and then load balancing, fault recovery. So we get it from those 2 systems. We are building SciSQL, which is a tiny set of user-defined functions for the spherical geometry, and then the Qserv, which is the magic that glues it all together. And we are also planning to run the MapReduce style analysis near the database. So we will provide access to the data through MapReduce style interface, and users will be able to access whatever they want to run if they can't do it through SQL. So the magic, Qserv. So we are really trying to focus on the things that we can't get off the shelf, at least not today. So things like the spatial indices, spatial partitioning, optimizations for spatial self-joins. We are working on the different schedulers, especially for the synchronized shared scans, synchronized between multiple tables that we go through at the same time. So Teradata has some things like this, but again, the price tag is a little bit too high. Custom metadata that makes sure that everything is all in sync. Fault tolerance that we are building on top of XLDB fault tolerance, which is actually not that hard because XLDB is covering a lot of the fault tolerance already. The tools for managing the cluster, which we need. And then we ended up with writing the SQL query parser because we need to rewrite the queries. And the analyzer and minimal optimizer, definitely only minimal. We are not going into full optimizer. We just know how hard it is. And again, we are using wherever possible, even within Qserv, so things like the protobufs, various protocols, interfaces. So the current status, we basically have it running. Most of what I discussed, we have the regular scans, aggregations, spatial self-joins with optimizations. We have fault recovery, basic shared scans. This is all implemented. We tried it on up to 100 terabyte data system. We tried it on 300 nodes. We tried 100,000 in-flight query fragments, run and manage at the same time. It's basically working. It's not a production quality. It's non-trivial to set up at the moment. And it is tuned for astronomy data. So we would call it stable early beta at the moment. So what's next? Few other projects and labs already expressed strong interest. Those are from astronomy. So we are planning to slowly grow the community. However, it really depends on how much demand they put on us. So we are very happy to collaborate with other communities who might be interested in reusing it. However, this is obviously funding driven because we are fully funded from astronomy, so we can't really work on the solutions that are just for biology or geoscience. And we would happily switch to open source if we find something adequate, and obviously we would have to look at the economics. So, take into the account how much that off-the-shelf would cost, but also we are looking into how much it costs to support what we are building in-house. So this is where we are, and yes, this was my last slide. So I think Mike is next, and he will tell us that we are all wrong and we should use something else. Where is Mike? Oh yes, that's Raghu. Right.